Swayam Prabha. Digital India. Educated India.
So there are three vectors. So among the three components. So if you are trying to project this vector along one of the directions, then what you will get? The component along the direction is what you would be getting, right? So similarly, I have a complete wave function which is like a vector. What I am trying to do is I am trying to project this wave function onto each of these atoms or atomic orbitals, to be very precise. When I am projecting this total wave function, what I solve always? I solve h psi is equals to p psi. So I will get the psi, and you all know that psi is the one that contains all the properties of the system, right? So I use this psi, I will project this vector. This is also called as wave vector. This vector I will be projecting onto the atomic orbitals of the cobalt, of the sulfur. Atomic orbitals of the cobalt and sulfur you can write as 1s, 2s, 2p, like that. When you project them, this is how the pictures will be coming. So how much of the overlap is there between this? So if I have a cobalt orbital, if I have cobalt 1s orbital, let us consider the 3d orbital. What I will be doing is I will be considering a 3d orbital and the psi. This is one notation of the product. Inner product you know, right? So you guys are doing. So that inner product or the dot product is what I have calculated. If I calculate, some number will come. Dot product is a scalar, so you will get some number. That number is what I am plotting here. Okay. When I plotted that number, this orange color line is coming like this. That means this guy has the maximum contribution. This is the total. I wanted to calculate the total by plotting it on the, for example, 2p projection I wanted to do, 1s projection I wanted to do, like this I wanted to do for each of the projections. So if you know there is a vector A which is along only the z direction, then what will happen? Along the other two directions, the components will be 0. So that means if this number is maximum and if these numbers are close to 0, what does that mean? The vector is actually orienting along that particular direction, right? Same way, this is the total DOS I have. When I am trying to project it onto the cobalt, onto the non-metal, it is showing that majority is coming from the cobalt. That means that is along that particular orientation only it is there. The total DOS here to the valence band. Till here majority is coming from the cobalt. There are some minor portions that are also coming from the X. Okay. So that's essentially the information. Why this information is useful for me? If I wanted to tune this system further, where should I tune it? If I wanted to tune the valence band, then I need to tune in the cobalt only. If I create a defect of the cobalt, then this band structure will immediately change. That is the point I wanted to further understand. For that we have drawn this. Okay, any other questions? You said,
So we discussed the three cases for like separation of conduction band and valence band for different material. What about for superconductors?
Completely different. Superconductors generally will be actually there can be metals also, metallic superconductors were also found. This is a completely different scenario. I cannot give such kind of a simple pictures. I don't have, okay. It's not that there is no simple picture. I am not the person working in that direction, so it is not. So even diamagnetic substances are necessary for you to, and it is based on the magnetism and other stuff, slightly different than this topic. So let's not mix those ones.
Sorry, again going back a bit.
Yeah, please go as much as possible, no issues.
So electrons are localized onto the X from the M on anti-mxenes.
Electrons are what?
You said the electrons from the metal are localized onto the non-metal. Is that localized onto the non-metal? Is that for both mxenes or only anti-mxenes?
No, so what we are trying to mention here is the kind of interaction. When you are considering the system, what kind of interaction is there between them. What we are observing for the anti-magazines is, it is there in this particular manner where the electrons are localized. Anti-magazines. If you study magazines also, you might most likely get the same kind of thing. That is not at all a big deal, because ionic type of interaction is there even in your sodium chloride. Right, Na plus Cl minus is what you are writing there. That is like an ionic type of interaction. That is not a big deal there. It's just to show that what kind, whether it is a covalent or an ionic is the only question. This is a solid. Solids are generally classified into covalent solids, ionic solids, van der Waals solids, and so on and so forth. For that reason we did that. Okay. Sir, how much time we have further? They are busy with something. How much more time we have? 12:30. Okay. Yeah. What I will do is, I will quickly show the slides, remaining ones, all of you. Only a few minutes I will quickly show the remaining slides so that you will have a feeling about them. Fine, madam. No issues. No issues. So I will quickly show that so that you will have a full picture of this. I will take the questions till the extent that it is feasible. Okay. Okay. So apart from this, what we need to also understand is about the adsorption. If the metal is strongly adsorbing, then it means that it will not allow you to form the dendrites. So now your system is there. How do you find the most stable adsorption site? There are several possible adsorption sites. We have considered like about 12 or so. Among them, 6 of them we could have able to optimize. These are the 6 positions we would able to keep. And among these 6 positions, we observed that S3, S1, S2, these are the 3 sites where the system is very stable. The other 3 are again coming back and falling back to the same things. So in this, the order of the adsorption is S3 greater than S1 greater than S2. So you just considered, these guys are not stopping talking. Please listen now, I am trying to explain for you guys only. Okay. So this S3 greater than S1 greater than S2 is what we observed. So you have several sites. For each site, you have different adsorption, and I am just ordering them. Which site is the most stable one is the one that I am finding. I found that S3 is the most stable site. Then immediately the question comes, why the S3 is the most stable site? For that we calculated what are called as the charge density difference plots, and from here what you can easily see is, this is the S3, this is the S1 and S2. S3, when you are putting this lithium atom at the S3 site, what it is happening is, the electron density is shared between 4 of the sites that are there. Okay, 4 non-metal sites. Whereas for the S2 there is only 2 sites that it is anchored. Whereas for the case of S1 it is like a single pillar type. So it is obvious that when 4 of people are holding it, obviously the central person will be stable. If only one guy is holding, it will not be. I will not take questions for some time. Please don't misunderstand. So this is how you are able to explain the charge density differences. Based on the charge density difference, you can clearly see the S3 site should be the most stable site. So that means when you are sprinkling these lithium ions on this particular material, where it will go and sit, it will go and sit at the S3 if possible. Wherever it is possible, first it will be preferentially, it will be sitting. This is very similar to if I am sending all of you inside this hall, where you will be sitting first. Will you sit on the floor or on the chair? Preferentially you will be sitting on the chair, because that is the most stable configuration for you for this kind of a class. If possible, you will also sleep, but that is not a sleeping place. So that way you will not do that. It's very similar to that here. So S3, S1, S2 are the 3 possible ways. S3 is the site that they will be going and sitting. But if S3s are done, maybe you will start sitting on that benches also, right? So that one is the S1 and so on and so forth. Okay. Next one, as I said, you want fast charge discharge. You wanted to charge your mobile phones. Within 30 minutes, it should go to 100%, but it should not discharge very quickly. So in order for this charging to be very quick, you need to, the mobility of the ion should be if the mobility of the ion should be high on this material, the migration energy barriers, if the ion has to move from one atom, position to another position. Right now you know that S3 sites are the most stable sites, like these chairs. If I ask you to move now, there will be a lot of chaos, right? So if you wanted to move from one chair to other, that is what is the amount of energy that I need to provide. If the energy is very minimal, if I told you all of you please move in a nice form, then she will be moving there, that person will be moving here, and so on and so forth. There is a clear movement for which the migration energy barrier or the barrier for the movement is very minimal. If the barrier for the movement is very minimal, then I can move very quickly. If the barrier for the movement is high, if I ask you to move like this, then everybody is moving everywhere. So the barrier is so high that the movement is not at all seen in the first place. Okay. So I calculated, or we calculated, this barriers for lithium ion motion, sodium ion motion and potassium ion motion on this particular surface, and what we observed was the motion is the least for the case of potassium. Okay. It is slightly a surprising thing because potassium is the one which is adsorbing strongly, but still we observed this. And these are the barriers for on different materials also. Whatever I have shown you is for one particular material, cobalt sulfide. Here I am showing you the barriers for various kinds of things. So the barriers for the diffusion is on the order of 0.2 electron volts to 0.8 electron volts or something like that. Okay, which is like reasonably good barrier, barrier in the sense it is the low barrier. So these ions can move quickly on this substance. Okay, that's all it is essentially saying. I wanted to ask this question, but because of the lack of time, I am not doing that. So the next one is it always only one layer of sodiums or lithiums will be adsorbed in between these two graphite layers, or in this case antimixene layers, or can I put more? The answer is you can put more, and generally that also will happen. So how do I identify whether it can be 2 layers, 3 layers or 4 layers, how many layers? Okay, that is again can be obtained based on the adsorption energies. If the adsorption energy after adsorbing 2 layers of this one is becoming positive, then I will stop. And there are also various other criteria with which I will stop this adsorption, and I will identify how many number of layers are there. I know I am going quickly, but because I wanted to take more questions and to discuss further. So apart from that, we need to calculate, as I said, anodic voltage we need to calculate. Anode voltage should be as low as possible. So how do you calculate this anode voltage using our calculations is you will write this kind of a reaction. So metal is there, metal is going on to this antimixene materials, and metal is going to bind to this antimixene material. That's all is the corresponding equation. Correspondingly, there will be a free energy. You guys have studied the free energies, right? So which is nothing but this particular voltage minus this particular voltage, or this particular energy minus this particular energy. That's what I am going to calculate, and which is nothing but the metal insertion voltage. And this metal insertion voltage, if you see the right hand side, this is the metal is adsorbed onto this antimixene. That is the full structure. I can calculate its energy. Left hand side, I have a antimixene. I can calculate its energy. I have a metal, I can calculate its energy. If I subtract the metal plus adsorbates energy from this only antimixene and also metal, I will immediately obtain the voltage value. That's what I am doing. So if I am calculating this voltage, if it is close to 0, then automatically it is more like an anode material itself, I mean the metal anode itself, and that is useful for me for high voltages, cathode minus anode voltages. Okay, this is again, I am just showing you the reasons for why just considering it, so I am leaving that. So by this, if I am considering, you can see for certain materials are reaching close to 0, certain others are going negative. So the ones that are going close to 0 are the ones which are good. Negative it is going means it's actually means there is some agglomeration between these ones and they are going to form the dendrites. So those are not useful for us. Only I wanted to consider the ones that are going close to 0. So accordingly, I think cobalt phosphide and cobalt silicide are the two ones that are becoming as promising anode materials for me. I have also calculated this specific charge capacity. How many number of atoms it can adsorb strongly per unit material mass. Okay, so if you are seeing this, generally the graphite is about 300 milliampere hour per gram, 330 or so something will be there. Here you can see that some of these materials can go up to 1000 for the lithium. For sodium it is about 600. For potassium also it is about, the maximum is roughly around 200, 300 something in between. Okay, so that means these materials can give actually better specific charge capacities. In turn it means it can give you the better energy densities if they are used instead of the graphite. But we need more calculations before asking our experimentalist to do that original cell, coin cell or something like that. We have considered after loading these materials, this is our antimixene. I have loaded up to 5 layers. So I wanted to test whether this is thermally stable or not, because my battery will become little bit hotter in summer. It will, if I am using more also it will be. So I study this temperature effects. When I study the temperature effects, again these are all simulations. Okay, don't assume that I am really heating the battery. I am just doing this. So here you can see that the energy fluctuations are very minimal, which means that battery, this loading is stable. If it is not, then the right hand structure will be showing you some agglomerates. The spherical type of particles might have come. That situation did not arise here, suggesting that it is stable at 300 Kelvin. Same goes for these other guys also. I was able to explain further why this is not changing for sodium and lithium, whereas for the potassium such things are failing. Why it is the case is what we have understood based on this electron localization plots, and then we calculated how much the interlayer spacing is going to increase when you are adding these lithium or sodium atoms, and we found that it is roughly okay. Okay, so that's all. I think I already showed you. So there I will end for this particular part. When time comes, another time, I will try to teach you some more about the PFAS and all these other things. I am open to questions. You had some questions and someone else also has some questions.
Sir, what are dendrites?
Again, as I said, dendrite by itself means like it's like a random growth. It is growing in all the possible directions. So like when you see the fractals, you heard of word fractals? No. So trees, when you see there is no leaves on the tree, how the growth we will see, I mean the structure, those are like fractal structures. Dendrites are like that kind of randomly they are growing into various what do you call shapes, that's all it is. In this particular case, it is like you have metal atoms, they are coalescing, forming like a sphere or something, and that another sphere is coming, these guys are interacting, they are forming like a tree branches type, these are growing in any form it is. Whether it could be like a nanowire or it could be like going into like in different directions, etc.
So just a doubt in the band structure diagram, that one you drew. You said when there's 20 of them, only 3 would go into the layer that has 5 slots available, right? Why is that? Yeah.
So originally we started with 20 electrons.
Yeah.
So you had here 3 levels,
Perfect.
3 2s are 6. Electrons are filled here. I think here I kept 4. 4 plus 4 2s, sorry, 4 levels means 4 2s are 8. 8 plus 6
so we're
is
taking them
14.
as pairs.
Huh?
We're taking them as pairs or?
Pairs, yeah, molecular orbitals is what I mentioned, right?
Oh. Thanks.
Yeah.
Few questions.
Yeah.
We had talked about how some sites are more stable in the case of when the ion goes and sits there. Would a more stable site mean the mobility from the site is lesser?
Very good question. That's the question I wanted to actually ask you. Okay, the answer is no. Okay, that's how we will generally feel. This is the slide I skipped, right? So if you see, I told you earlier that among the 3 atoms, potassium, sodium and the lithium, which one has the highest adsorption energy? Potassium has the highest adsorption energy and it has the least migration energy barrier. The reason for this is, it's not about how strongly it is binding. It's about overall structure here you need to see. So whether, I mean overall structure in the sense, if I am having 3 sites, if the energy difference between the site 1 and site 2 is very little, then the migration energy barrier will be less. Again, if this person has to get up from this site and go to the next site, if the difference between the sites is very less, then it is easy for the person to move from this place to the other place. It's not about how comfortable it is. How easy to move is the question we are asking. Okay.
So it's about the difference in energies
It
at
is
S3, S1 and S2.
Very good, that's all. It is that particular part. S3, S1, S2 differences, if they are low, the migration energy barrier will be low. On the other hand, so that values also I have given here, these ones, I think you guys are able to see from there. So if you see for anyone, if you focus here, difference between these two, for example, S3 to S1, it is like 0.4 roughly, minus 1.68 and minus 1.28 you can consider. This is like 0.4, whereas between these two, 1.3 and 0.7 is like 0.6. So obviously potassium should have a quicker transfer, I mean easy migration. And between these two, if you see minus 1.5 and 0.7, that is like about 0.8, right? Yeah, 0.8 barrier. Okay, so that's the difference in the barrier, difference in the energies between the sites is the important thing. That's what I tried to show here and that's how I explained, but I think you guys got the major point. Yeah. Am I blocking you? Sorry.
Also, is there any way we'll get access to these slides?
You can get the access. I have already uploaded similar kind of videos also on the YouTube. So, okay, fine. Yes.
Sir, could you please repeat the reason why although potassium has the least energy barrier, why is it showing the slow motion that you were telling? Which was surprising, you
It's
told
not
me.
slow motion.
Sorry, it's not showing least mobility.
No, neither that. I said that it has the least migration energy barrier. That means it will be easily moving. So, migration energy barrier. So, the barrier that is there for the migration or the movement is low. That means that potassium atom is able to move easily, is the point I am trying to say. The what you call counterintuitive thing here is potassium is the one that is binding strongly to the system. What we would generally assume is if something is binding strongly to the system, that will not be moving at all, right? That will be strongly held there. What I am trying to show here is even when it is strongly bound, it can easily move to the next one provided the difference between these two is less. Okay, the absorption energy difference between this site and the next site, if that difference is less, so then what is the barrier for me? I just need to move little bit only. Whereas if the difference between them is very high, so it is like asking you guys to move from one seat to seat. Obviously, because the seats are roughly the same, the difference between them is very little. So for your motion, it will be very simple. Okay. On the other hand, if I ask you to sit on the bench that is there, that is having a higher barrier because that is not similar. Sitting on a bench versus sitting on a chair is different. So that difference, when it is more, you will need a lot of motion to happen. Here you can just sit on this and just simply move like this. There it is not like that. That's all I am trying to mention. Although what is the most comfortable position for you is in the chair only. That is S3 side, it is very strongly binding, but because the next side is very similar, I can simply move from one side to the other.
How do you actually simulate the thermal effects, sir?
Thermal effects are simulated based on what are known as the classical molecular dynamics we will be doing in this case. So this is a variant of the time dependent Schrodinger equation. Okay. I know that I am just pouring some words here. The best way to tell you is about thermal or temperature effect means what? You have some kind of related motion is what we are including. So there are some things called baths which will give you this temperature. BATH bath, not only this bath, this is like a set of atoms is called as also bath. These are called as these are called thermostats. They will be able to control the temperature within the system, which itself is dependent on the motion. So motion is the one that is producing the heat or the temperature to you. So somewhat related along those lines. So even more what I can tell, kinetic energy is another parameter that you can think of in terms of the temperature. If you have larger the temperature, larger will be the motion. So thermal effects here is about if I am giving 300 Kelvin temperature to the system, okay, which is coming again based on the statistical thermodynamics that you will be learning little later. And the statistical thermodynamics is telling more about what is the distribution, how this, if I am giving this much energy to the system, how it is distributed among all the atoms. So if I am giving 300 Kelvin temperature to the system, that is like an energy, how this 300 Kelvin temperature will be distributed among all the atoms that are present in the system. If this distribution is weird somehow, then what will happen is these atoms will try to coalesce or something. Okay, so you will be learning what is called as the Boltzmann distribution also very soon. That is telling you about how this energy will be distributed among these energy levels, etc. But beyond that, I don't know how to simplify it very quickly. Right now, in my head, I am not having the picture to give you very quickly. But essentially these are the things it will happen. So when you are trying to see how the temperature is included through kinetic energy of the system. Okay. The temperature is maintained through some of these thermostats. They themselves are again related to the motion. Harmonic oscillators they will be considering and they will be putting it there. What else I should say? That's all. Essentially those two are the things that will be dictating the temperature of the system. But it is sufficient for you to understand that it is coming from the kinetic energy of these molecules. Why I refer to the classical molecular dynamics is motion, what you are doing here of the nuclei is always dealt in the classical manner. This is not quantum mechanical motion. Okay, that's the major thing. So if you wanted, whenever you are picturizing this carbon atom, again you are picturizing the carbon atom as a particle. All of us, right? That is also wrong. That is not true. But that is most of the times it is correct. That's the reason we are assuming them as like point particles, like classical particles, and their motion is simply dictated based on the nuclear Newtonian equations of motion, F equals to ma, that you have. From the force is also, you might remember minus dp by dt, right? Or gradient of the negative gradient of the potential energy surface is like the force. I have shown you how to compute this potential energy surface for the distance. If it is between the two hydrogen atoms, if it is moving, you can draw a potential energy curve, right? Similar way, I have shown you that three-dimensional potential energy surface. If you calculate the gradient of the potential energy surface, that will give you the forces acting on the nuclei, and those motions are the ones that you will be computing every time using according to F equals to ma type. Okay, so nuclei are moving. This movement corresponds to the kinetic energy, and the kinetic energy will correspond to the temperature. This is the long story. Energy is computed as based on the Schrodinger equation. It's I is equals to E psi. That E is the one which is you are calling as the potential energy. Gradient of that potential energy will give you the forces for each of the atomic nuclei. Okay, so each nuclei will have this specific force dictated by that potential energy. Whether if you are at the top of the potential energy surface, the force will be very high such that it will come down. Okay, not this slope. You should be thinking in terms of the force acting on it. Okay, will be very high because it is the negative gradient. Okay, so that will come down, and at the equilibrium forces will be zero. So this motion, whatever it is there, that motion is giving you the kinetic energy to the classical particles here, which are the nuclei. The motion is nothing but the kinetic energy, and kinetic energy is related to the temperature. That's how the temperatural effects are there, and that is the thermal effects essentially. Temperature is the thermal effect which we are trying to speak. But I said in a different manner, but that's all essentially it will go in terms of the equations there.
A clarification. So the eigenvalues is for the second derivative, what operator? Like,
so this is not operator, this is the matrix. Eigenvalues of the Hessian matrix. Yeah, so a Hessian matrix you are easily generating. How do you generate the Hessian matrix? Dou square E by dou Qi dou Qj. Right? Qi and Qj corresponds to two different coordinates. One is angle, another one is distance for simplicity. Same R, you can have multiple R's also. So if you have 9 coordinates, you will get 9 cross 9 matrix. The 9 cross 9 matrix you get, you need to diagonalize that 9 cross 9 matrix. Maybe you are not equipped with the ways of diagonalizing, but you will learn some numerical way to do that 9 cross 9 diagonalization, which will give you the eigenvalues. Those eigenvalues are nothing but your force constants. If any eigenvalue is coming negative, then immediately you are able to understand that this is something different. It is like a saddle point. It is not. K is the eigenvalue. Yes.
How did you get 9 coordinates, sir?
9 what?
9 coordinates. You just said.
No, I just said, like, if see, for hydrogen molecule it is 1 coordinate. So immediately I can solve. The K is the equation we have solved earlier. No, K is nothing but dou square Q by dou square E by dou R. R is the internuclear distance. If you simply calculate that, the minimum is nothing but your equilibrium distance.
So is this based on the orbitals or?
No, I already explained. Can anyone tell me how do we define the number of number of coordinates? Yeah, how you are saying 3m?
each atom has.
If there are n particles, each particle can have 3 directions of motion, x direction, y direction and z direction. This can move along any one of these directions. So if n particles are there, all of them can have 3n motion. So there are 3n possibilities for us to tune. 3n possibilities we are tuning and finding what is the best one for that. 4. No more questions? No, good. Ask more questions.
Sir, I was not able to understand as you went a little fast in this particular place. The number of layers coated on the electrodes, how did you calculate that, sir?
So again, number of layers, you will just load. The loading is, loading is not also a bad word. You will absorb more number of layers. It's not a big deal because all I need to do is place the atoms there in those positions, okay. I need to identify how many number of layers I can absorb, okay. That is what I am trying to see. If the absorption itself is becoming negative, then I am stopping there. So why I am doing that? So absorption negative means what? As I said earlier, energy going to be negative always is stable. Okay, like a pit. If you are digging a pit, automatically water will go there. So if there is a negative energy for you, then definitely electrons will be going there. Okay, so that is a stability, indication of stability. The moment my absorption energy is positive, that means I cannot go further. If I add one more metal, metal and metal will interact. There will be no interaction between the metal and the adsorbate anymore. So I will try to load one layer first. I will check the absorption energy, average absorption energy per atom. If it is negative, I will start for the second layer loading. If it is still negative, I will go to the third. If it is positive, I will stop at the second and I will say that only maximum of 2 layers can be loaded. This is useful for me in order to calculate the capacity, because if there are 3 layers, that means per gram of material I can load more number. If it is only 2 layers, it is little less. If it is only 1 layer, very less. So that is telling me about the specific capacity of the system.
Thank you.
Welcome. Go ahead.
My doubt is pretty similar, so you've already answered my question.
Cool. Sure. Any more questions that are popping up and down in the heads? Okay. Yeah, I will be here anyway, so you are welcome. If when you are going through the slides or if you have time, if you are working with me, you can always come. I'm just sitting down from here, you can see me also. So come to me and ask me the questions if you have more. Thank you. Bye.
Thank you so much for the amazing lecture, sir, and thanks for taking time out of your busy schedule and coming for us. It's a pleasure to have you.
Okay, thank you.
A deepest gratitude from everyone.